Hello, my name is Gonzalo Abad, and in this tutorial we are going to see how can be made the implementation and control of a double-fifth induction machine in Matlab-Simulink. All the theory on many details about this issue can be found in this book, Power Electronics for Renewable Energy Systems, Transportation and Industry Applications. More specifically, in this book, there is one chapter, which is chapter 10, which is called Properties and Control of Double-Fifth Induction Machine. So we are going to base this tutorial on this chapter. So first of all, what we need is to open MATLAB, and then we need to create a new file, model, in Matlab-Simulink that we can call, for instance, like this. We open the model, and once we have opened the model, we can create all the system. We can open the Simulink library browser, and what we need to create in chapter 10 of this book is here. This is the power circuit in which we have the double-fifth induction machine. Here we have the power electronic converter, a back-to-back power electronic converter, and here each converter we need to create the rotor side control and the grid side control. In this case, we are going to only implement the rotor side control for the control of the double-fifth induction machine. So let's start creating the model, and in order to do that we are going to use the SimEscape library. And here we have the power system library, and here we have the specialized technology. So we will work with the models already created in this library. So what do we need? We need to go to the fundamental blocks, and there, first of all, for instance, we need machines. So this is the machine that we need. Then we need also sources. Let's take this one for instance. So there we have the three-phase voltage source. There it is. We see here that we need a neutral point, so let's find it. It should be here. Let's connect to the ground. Then later we will need to measure at the stator side voltages and currents. Therefore, we need to put just in the middle for instance, this measurer in which we will use a label, we will use face to ground. Let's call to the voltage like this, and let's call to the current, to the stator current, like this. Okay, so let's connect the elements little by little, one by one. At the beginning, just we use a constant input for the torque that can be found in the general Simulink library, for instance from here. We can take it there. Sorry. Let's do it smaller. And let's put just 0 at the torque, at the low torque. Then at the rotor, we need the power electronic converter, which should be somewhere here. So let's find it. So let's use from the very options that we have. Let's use, for instance, this one from here, and let's use ideal switches. Let's put there here as well the default values for the snubber capacitance, resistance, and so on. So let's connect it. Sorry. We will need another measurement in the middle. So let's put it there. Okay. And we won't use the voltage in this here, and let's call to the rotor current like this. Sorry. Let's do it in that way. Okay. And then, as I have said before, we won't use the grid state converter, so we will simplify the system and we will just put a DC voltage source. A DC voltage source that we can find it here. Like there and like there. Sorry. So we won't use voltage measurements. So there we have the voltage source. Okay, and we need to control the voltage source converter by means of a PWM modulation. That modulation can be found also in For instance, here we have a set of different modulations, blocks. So let's use this one in here, and let's connect it to the system, to the power electronic converter. So this is the system, the power electronic circuit that we have. So let's use now, so let's put the names on the parameters of the different elements that we have here. For that purpose, we have already made one .m initialization program, which is here. Let's put it there. And we have already all the parameters of a 2 megawatts stator power double feed induction generator. There we have the voltages, currents, torque, parameters, the DC boost voltage, and so on. There you can have some more details. Okay. So let's, for instance, start from the double feed induction generator, and let's put the parameters. That will be the rated power of the stator. That will be UBS. That will be the frequency. There we need to put the stator resistance, analyze leakage inductance, and something very similar to the rotor. Please keep in mind that this rotor resistance is referred to the stator, and in this case we have a machine which has a stator and rotor turns ratio of this value, 1/3. This is the magnetizing inductance. There we have the mechanical parameters. This is the inertia, this is the damping, and the pole pairs are 2. As initial conditions, this is the initial sleep condition. Let's start from 1, what means that the machine will start from speed 0. And that's all. Sorry, we didn't initialize these parameters to the Matlab. Now we have the parameters. We can see them there. So there is here another error. Yes, now it works. For the grid voltage source, we need to specify the voltage amplitude. That should be the same as the machine voltage amplitude. Then the frequency as well should be the same. And in this case, if I'm not wrong, this is the frequency that we have chosen, 50 Hz. And let's choose, for instance, the phase at 0 degrees. The voltage source, the power electronic converter is already fixed. There we have the DC boost voltage that can be calculated according to this formula. And finally, here we have the PWM generator, where the frequency, the switching frequency, that we are going to choose is this value, 4 kilohertz, which is a quite high value, but anyway, 6 pulses. And the sampling technique that we are going to use is single edge, symmetrical. So with this, we have all the power circuit already created. I don't really like to see too much the block names, so let's eliminate the block names. This is up to you, obviously. This is just a matter of style. And that's it, our power circuit. Okay, so the next thing that we have to implement is just the control. The one block, we can put here one block which controls the whole or the entire system. So for that purpose, we need the Simulink library. Let's take, for instance, one block like this, and let's create a subsystem, Control G, like this. And this will be the control block. We need some inputs that can be found here. We can copy them and put, put them there. So we need more than one entrance, like in here, and the block takes this shape. So the control strategy that we are going to implement for the control of the double feed induction motor is based on a vector control strategy. All the theory can be found in this book and is represented with this block diagram, in which here we only have the current loops. So let's start from here. Okay. But later we will need to add here another 2 loops, well, 2 or 1 loops at least, in order to control the speed of the shaft of the machine. And that will be this control block diagram. But let's start from here. So here we will need as entrances, let's do bigger, a speed reference, we need also ID current reference, and then as measurements we will need, if I'm not wrong, a stator current, rotor current, stator voltage, rotor currents, and theta angle, and speed later for the control of the speed. Okay, so there we have the block. for the control. At the beginning, let's take a constant. Let's start from zero. Let's remove also the block name. Sorry. Let's put 0 reference for both, and then here we need these measurements. So we need some front tools. That should be somewhere here. Sorry, I couldn't find them. Signal routing, maybe. Yes. This is one. Remove the name. So one of them should be stator voltage. Let's put it there, and it was coming from there. Let's put also rotor currents. IR. That should be there. Okay, and then we need the theta angle of the shaft and the speed of the shaft. That will be taken from there. For that purpose, we need a bus selector. We can group it, Ctrl G. Just connect there. Remove the name, and we don't really need outputs. I think it's more comfortable to use go-tos. So we go to signal routing and we take one go-to like this. And let's call theta to the angle. Sorry, let's do it global. This is one, and the other one will be, let's have a look. From the bus selector, we need to go to the mechanical parameters, and first of all, we select the rotor angle theta. We don't need these signals anymore, so that will be the first output. And then we need the rotor speed, which is in radians per second, and it's mechanical. So let's add here, and it will be the second output. Theta angle first, and then let's call it omega m. We can make it a little bit bigger since we have space. And those are the measurements. That was global, yes, okay. This is theta. Okay. And this is the speed, omega n. We can make a little bit bigger just to see the label. Okay. So there we have all the inputs and outputs that we need. And for the outputs, obviously this is not correct. That will be the stator voltage references. So let's call them like this. So let's move forward. But before we do that, let's have a look again of the block diagram that we need to implement. We will start from this side, implementing these blocks. But first, please take into consideration that these blocks or this normalization is not necessary, because the W5 inductive machine model of the SimPower library is or presents the rotor referred to the stator. So this normalization is not necessary. So the first things that we need to implement are these transformations. So let's go back to our file. And in this case, we have already prepared one library in which we will have all the blocks, all the transformations that we need. So this was the first one that we need, if I'm not wrong. Yes. We place it here. But please keep in mind that as we have the PWM modulation block and it uses the triangular waveforms normalized 1, this output must be also normalized. So we need again, like for instance here, just at the output, normalizing according to our DC boost voltage at the converter. Okay. Then we also need a DQ transformation. Sorry, before that, let's mention that in this case, that will be, sorry, D and Q transformation to ABC. The mathematical transformation is equivalent to this one presented here and can be implemented by using just functions like this. So this is one transformation, and then we need to transform this block. That again, we go to the library, which is there, and we need to take this one, this block, take it there, just connect, and again, this is how it has been implemented. Please keep in mind here that now we need theta angle. Okay, and this matrix transformation is implemented there by means of function from Matlab. Okay, so the rest two transformations are necessary for the rotor current. Therefore, let's take them from the library, copy and paste. Sorry, again, this name is not correct. This is Q. And this is D. And this is the matrix transformation. and this is the last transformation. How is it implemented? Okay. It is very advisable to use here a third harmonic injection procedure in order to extract more voltage for a given DC boost voltage of the power electronic converter. This block is also already prepared in here in the library. We take it there. And this is a very simple block that allows us to be able to increase a 15% of the output voltage for a given DC boost voltage. This block is very simple to implement. Okay, let's have a look again. So we already have, this part, more or less. We need this angle, theta angle, and we need the angle for the transformations. So we need to implement this block. So let's take, for instance, this element and make a group. We need also an input. So we need theta m angle that can be taken from there. Then also we need the stator voltages. Therefore we need another input. Then also we need one transformation. Let's take it there. Let's connect there. That will be the output, theta R. I was saying that we need this transformation for the stator voltages, but in this case, since they are stator voltages, the output voltages will be in alpha beta. And from these voltages in alpha beta, or a stationary reference frame, we can directly calculate the angle theta of the stator voltages. But for doing that, we need another block. I think it's this one. And we need to implement it's not this one. Better this one here. So from these angles we need a multiplexer, I guess. A demultiplexer, and the division which is made is beta over alpha. Let's remove again this. So that will be this angle, that in this case we didn't use the PLL, we are using a simple atan2 function. Then we need to subtract 90 degrees. We have this angle, we need to subtract more or less 90 degrees in order to get the angle of the stator flux. So we need another block. For instance, this one. We connect it, and we need one constant. We have lost the constant. Okay, so let's take it there. Pi over 2, and that should be subtracting. So this is theta S. Again, we need to subtract this angle to theta m, and therefore we get theta. Sorry, this angle was in mechanical radians, therefore we need one gain, such as for instance this one. Now, therefore we need to multiply by the pole pairs in order to have this angle in electrical radians. This is electrical as well. So this is the theta r angle estimation block, which is used there. Let's do it bigger. And it is also used there. Okay, once we have this, we have this side already built. Therefore, we need two regulators and we need these currents. Again, if we go to the library, which is there, we have already prepared one block for a PI controller. We placed it there. So once it's going to be used for ID regulator, that output should be there. Let's do a little bit smaller. So here we should put the gains of the current regulators, Kp and Ki, which can be calculated according to this tuning procedure that we have here. So this is the constant gain, and this is the integral gain. Let's have a look to the integrator. Initial condition could be 0. The sampling time should be the inverse of the switching frequency. and we can use a saturation that should be this value in negative in the lower, and at the upper should be positive. Okay, I think that's everything correct. And here the saturation again should be this value for the positive and this value for the lower limit. So this is the PI controller for the ID current. We can use something similar for the IQ current. Let's do this. Sorry, this is not correct. We will need more space there. This will be IQ current PI controller, which is exactly the same to this one. TT. So this is the current. This should go down. We need a little bit more space there. There. This is DQ current that should go to those two PI regulators. Okay, so let's have a look again of the block diagram. We need to cancel now this coupling term. This is quite complex formulation, so we need to go again to the library because I have already prepared, sorry, not here, but here we have already one block that we bring it there, and there you can see how this cancellation can be made according to calculation of omega r from omega s and from omega m in electrical radians. And then we implement, just by using this type of equations, these two cancellations, which are these cancellations. So this should be located just in the middle there. And these are the outputs, and omega which is the speed, should be taken just from there. Okay, we need, if you realize here we are using some front two blocks for these currents. We need to create the corresponding go-tos. For doing that, what we need is again to go to the Simulink library, and in this case we need some go-tos, globals, and we need IDR. Okay, and IQR. We can place them both here, for instance. No, maybe they could be. For instance, if we use a multiplexer, that could be, no, not this one, sorry. This one in here. There we have IDR and AQR. And from here we need more space. So let's move all this part more or less there. So this is ID and this is IQ. Let's move them like there. Let's do it a little bit smaller. Sorry. Opa. This is IDR and this is, sorry. IQR. So these are the two go-tos and these are the two corresponding front-tos. We need to create, because later we will need the voltage references. Let's call them ref, for instance. That will be one, and this one in here will be the second one, and this will be Q. Okay. These are the cancellation of the coupling terms. And once we have this, if I'm not wrong, we have already all these current loops already prepared. Therefore, we need to pass to the next block diagram in which we are only going to add this speed regulator loop. Okay, we will let this reactive power compensator or regulator, we will not implement. So we are going to only implement this one in here. Therefore, we need to prepare this gain and we need also another regulator. The speed reference is here. We need the last regulator. Here again, we need to go there and the PA regulators gain should be located there. Okay. Initial condition could be 0, the sample time as before, that one, and we can limit the output of the regulator to, in this case, the rated torque, because the meaning of this output regulator of the speed is the torque. Therefore, this is the rated torque in positive value and in negative value. And the same should be made for this saturation block. and this is the regulator. The speed is coming here. Just remember that this was mechanical speed. These are the regulator gains, which are calculated according to this formula. And now we need a gain, such as this one. We need to divide by this constant gain. Let's move it there to make things easier. So we need to divide this output, therefore, sorry, let's have a look again. Yes, we can place one easy gain, such as, for instance, this one. We copy it again to there. That will be torque, and this will be IQR, sorry, and we need to connect it there. And obviously this should be 1 over minus 1.5 multiplied by pi by Lm over Ls multiplied by Fs, if I'm not wrong. Sorry, this should be within. Let's do it bigger, just for checking. Yes. And this is the constant. Okay. Yes. It seems that everything is correct. So we can make this gain a little bit smaller. We don't need this anymore, so we can save, and this will be the reference. Yes, so this is almost finished. This is the control block diagram. That should be this one without this regulator. Okay, so now we need to visualize the different variables that we need to check in order to understand if the system that we have created is working properly or not. So we need to use from the Simulink library scopes. That should be somewhere here, this type of blocks. Okay, I have again already prepared in my library one monitor block that I will copy from here to my system, and I will leave it there. And here we have already prepared, we have already some go-tos and for visualization. Here we have with bigger, so there you can see some variables and some from-tos. So what we need is to place in our system the remaining go-tos. So let's go again to the control strategy. Which is there. And what we need this reference IDR reference that will be for this loop, and for this other loop we could locate it, sorry, for instance there. That will be Q. Okay, we have these voltages, currents. What else do we need? Okay, we need the speed references. Omega reference. It is useful also to see the torque reference. So let's call it, for instance, like this, torque omega. And we will need, I will copy it from the machine parameters and the mechanical part. We need the electromagnetic torque, okay, which is the actual torque, the real torque. This is not used for control, but this is just used for watching it. So this is torque, which is coming from here. Okay, so let's have a look of these variables. Okay, omega r, omega m. Omega m was, if I'm not wrong, here. Omega ref was there. IQ ref, V ref. Those two are here. What else? The torques. US, ES, here. Okay, so I think that everything is there. And we can name these elements. I think is there. So the display signal for one is speed. Apply. Okay, and this is the name there. So we do the same for the rest. Number 2 should be this one, and that will be IQ. Reference with its actual value. Apply. There we go. Number 3 is this. Sorry. Apply. Number 4 is torque. Let's call it like this. Torque. Apply. Number 5 is ID. Okay. Number 6 is VQ. Number 7 is stator voltage. Number 8 is stator current. Okay. And last, number 9 rotor current. So everything is there. Okay. We can save it. Let's better move to this side. So this is our system. Some more space. Okay. It is very recommendable to use here zero order holders in order to make the system work as close to the reality. Sorry, this is 0. Now I see the low torque. So we need to go to Simulink library. Let's put it there. We need to go to this place, and somewhere there should be the zero order hold. One over the switching frequency, which is also the sample time of the control that we are implementing. So at each measurement, we just copy there. All the elements, they present constant sample time. Therefore, here, as you remember, all the PA controllers were at sample time 1 over the switching frequency. Therefore, the whole control strategy is working at this sample time. So if I'm not wrong, everything should be already prepared. So let's load again, just in case, the initialization program in which we load all the variables. That should be here. Yes, okay. So now we need to put here, for instance, one current reference to 0, and here we can place one speed reference that should be, for instance, if this is the rated frequency, let's do, for instance, for example, 90% of that value. So that value should be more or less 141 radians per second of rotational speed in mechanicals. Okay. So let's start the simulation. Sorry, I have forgotten the power key block that must be taken from the Simulink library. should be opened somewhere there. This block is compulsory and should be there, for instance. It's very recommendable to use TS and discrete sample time. So we can start and let's see what happens. It seems that there is no speed control because there is no torque control and so on. So there is something wrong in the system. Let's have a look. Yes. This block is just taking positive currents going out from the machine to the converter. And positive should be just in the other way around. Positive should be from the converter to the motor. Therefore, we need to change this block by yes, so now it's just in the other way around. And the same for this, but this is not so important because we are not using currents for the control, but anyway. So first, flip the block and then clockwise. And oh, sorry, this was okay. This was properly connected. Sorry. Now it should be better. However, just in case, let's check again the control strategy. Yes, this is not possible. Obviously, the normalization should be divided, not multiplied. Otherwise, we are not obtaining here sinusoidal references between 0 and 1, between -1 and 1. Okay. So save again. And let's see what happens. Now the speed is going up. Slowly, slowly. The strong perturbation that is caused because we are starting the machine directly connected to the grid, which is not in practical situation mates, but you see. For these simulation purposes, we are not doing properly a very correct startup, but once this startup is reached, we see that the system is controlling properly. We have some oscillations at the speed, but more or less in 1 second, a little bit more time, it seems that everything is correct. We can just pause the simulation and see what is happening. There we have the torque, there we have the speed, there we have the IQ, ID, these are the voltage references, and these are the currents. Okay, that it seems that everything is correct. So now, for instance, let's put, this is the rated load. So for instance, 25% of the load in positive. And let's continue simulating. Yes. Therefore, we see that the torque is moving because of the load that we have changed, and that has been a perturbation for the speed. Okay, it seems that everything is correct. Here we have the difference of frequencies between the stator and rotor currents. Let's move, for instance, now the speed reference to the synchronous speed. Therefore, here we see the step reference change, and here we are approaching to this speed reference. There is an overshoot. There is an overshoot there. Here it is the torque working, but the speed is going to the reference little by little. And here now at this speed, at this synchronous speed, here we can see how the rotor currents are almost DC. They are not sinusoidal. At this operating point, the machine, the double-fifth induction machine, is working as a synchronous motor with DC currents at the rotor. Okay, let's change something again. For instance, let's move to hypersynchronous operation. So here it is, the speed step change again. There we have the rated torque during the transient. And from here, again, we should have an overshoot that will go down again, 2 radians per second, more or less, of overshoot. Let's wait a little bit until the steady state is reached. Here is a short oscillation of the speed, but now we can say that we are almost at the steady state. So finally, let's change from motor operation to generator operation by changing strongly the low torque. Now it becomes negative. That causes a strong perturbation at the torque, and therefore the IQ current is also working. But after some few milliseconds, the steady state will be reached as well. Again. So more or less there we have again the steady state at 6 seconds more or less. Let's stop the simulation and we can now analyze once we have finished these simulations what it has happened. Let's remark again that this startup is not very properly made in terms of that in reality we cannot do that, but for sake of simplicity we have avoided this startup. So let's pay attention to what happens after that. For instance, here there we have the speed variations that we have performed at the reference and therefore at the actual speed. There we have the torque that has been modified accordingly. Therefore, the IQ current has been also modified accordingly to the torque. That should be in the other way around. That will be IQ, the voltage reference, according to more or less this current Q variations. For the ID current reference, we have maintained all the time at 0, therefore the voltage reference has been also more or less 0. The stator currents have been like this, and the rotor currents have been more or less like this. For instance, here we have synchronous operations. Here we have synchronous operations because we are lower than the synchronous speeds. Therefore, here we have, ABC sequence. Here we were more or less at synchronous speed. Here we have DC currents, and here we have hypersynchronous operations. Therefore, we have here ACB sequence. Let's check it there with more detail. ABC. Little by little. And there we have ACB. Okay, we can see with more detail this sequence. Okay, these are the currents of this stator, 50 Hz, and these are the voltages. And these are the current loops performances, and this is how accurate can we achieve the speed control and the current loops control. Here it is, the accuracy of the torque. Okay, we have already implemented the double feed induction machine control, and we have made the machine operate at different operating points. I hope it was useful for you, and thank you for your attention.